Hello and welcome to this first session on symmetry in chemistry. And I really wanted to open up with some kind of motivational ideas about why to study this at all. And starting off with a kind of aesthetic one, looking at this first slide here, and that is that in considerations of beauty and aesthetics, symmetry is a key part. And so, there's something naturally appealing about symmetry. And it appeals to us actually on more than a visual level, but even on a kind of elegant mathematical level. And so looking at this a bit further, on this slide here, I talk about appeals to symmetry and how it goes back really to antiquity and yet also is relevant to the modern day as well. So those pictures there, we've got Plato on the left there and his Platonic solids, the 5 Platonic solids, these being the most symmetrical solid things, that's to say all the vertices equivalent, all the edges equivalent, and all the faces equivalent, and there are only 5 of these three-dimensional shapes, and you can see there in the picture of these dice. So, if you've ever played role-playing games and things, you might have enjoyed rolling dice like this. And so our Platonic shapes here, these were taken very seriously, so much so that, again, appealing to this kind of symmetry, Plato felt that they had to in some way represent the basic elements as they were understood at the time. And in more recent times, Kepler thought the fact that there were 5 observable extraterrestrial planets must relate in some way to the Platonic solids. And so he was thinking in terms of the planets kind of in relation to Platonic solids. So, there seems to be this kind of desire to equate our understanding of the world to these symmetries. And the kind of modern version of this is Murray Gell-Mann, we see illustrated there. He really developed our quark model. And so, we know that quarks are the kind of fundamental building blocks that make up protons and neutrons. And Gell-Mann dreamt up this phenomenal theory of quarks, despite the fact that no one had ever observed a quark. And in fact, what was observed, there were very large numbers of these fundamental particles, or these sort of nuclear particles being discovered in the 50s and 60s, so much so that there were so many of them, it just seemed bizarre what could possibly explain them all. And it was really Gell-Mann's genius. He was able to take all of these different particle observations and came up with a scheme, again based on symmetry, and admittedly it was quite a kind of abstract mathematical argument, but ultimately it was based on symmetry. And so you might have come across the eightfold way, which was one of his kind of symmetrical arguments. And in fact the amazing thing was, not only did he categorize all of these newly discovered particles, but his model actually went on to predict the properties of a particle that might be detected in the future, and indeed it was detected. And he went on and got the Nobel Prize, and it was brilliant. A little bit like Mendeleev, looking at all the known elements, coming up with the periodic table, there being gaps in the table, him predicting the properties of an element to be discovered, and elements being discovered, this sort of thing. Very nice story. So going on to our motivations about studying symmetry, and it turns out to be surprisingly powerful in simplifying problems, not just in chemistry. But the approach we're going to take to begin with is just looking at molecules and the symmetry of those molecules in terms of elements and operations. So you can see here, we've got a lovely symmetrical looking building there on the screen, and also we've got a couple of depictions of water molecules in the context of symmetry. And so the two sort of obvious types of symmetry we'll begin by looking at are rotations and reflections. And so what we can see on the picture here, we have this symmetry element, so that's some property that you associate with the symmetry, like the axis around which you rotate a molecule, or the plane in which you reflect a molecule. And then we also talk here about the operations of the rotating and the reflecting. And the point is about these operations is that once you do the operation, the molecule appears as it did before. That's really what we mean by symmetry, that leaves the molecule looking unchanged. And one thing that's quite neat about this is that we often talk in terms of symmetry labels without even realizing it. So curiously, when we talk about s, p, d and f orbitals, these are in fact symmetry labels. And when you talk about sigma and pi bonds, you might think about it as head-on overlap and side-base overlap, but these are actually quite technical symmetry terms. So they sort of infuse all through chemistry, these symmetry terms. And you can actually take this beyond the kind of sort of obvious ideas of reflecting and rotating in three-dimensional space. Even in the kind of more abstract mathematical world of looking at wave functions and integrals, again, you can use arguments based on symmetry to make life a lot easier. Specifically, you can often take extremely complicated looking calculations and use a symmetry argument to deduce that the result has to be precisely zero. And this is a brilliant time-saving device. And so now on to these symmetry elements and operations. And well, we saw water before, where you had a kind of twofold rotation. And in fact, we see on the illustration here what we might refer to as threefold symmetry, both of these pictures. And so introducing a bit of notation here, it's the so-called C3 rotation, or the C3 rotation axis. So C there really denoting rotation, and the 3 talking about the kind of n-foldness of it. So in both of these cases we've got an axis, if you like, perpendicular to the page, perpendicular to the screen, and if you rotate it around 1/3 of a rotation, you return the object to its original state. And so there we go. If you've got a rotation axis of order n, then if you rotate the object 360 degrees divided by n, it leaves it looking unchanged. And so again, the symmetry axis is the element, so it's a kind of feature of the symmetry of the molecule. Whereas by contrast, the actual act of doing the rotation, or the reflection or whatever, is the so-called symmetry operation. We can think of it actually moving the object. And one curious thing is that these two are not really quite equivalent, and actually C3 is a nice example of this, because there's one C3 axis, but there are two types of operation you can do with the C3 axis. That's to say, you could rotate by 120 degrees, or you could rotate by 240 degrees. And so these are two types of symmetry operation associated with one symmetry element. Now let's have some practice with benzene. We're asking ourselves, how many rotation symmetry elements does benzene have? In other words, how many rotation axes are there? So looking at the molecule, the obvious thing that you see first away is the six-fold nature of the molecule. So you might say straight away, well, it's just a C6 axis. But there's actually a bit more to it than that, because if you think about it, if you apply that C6 operation twice, 120 degrees, you could call that the result of a C3 axis. And if you applied the C6 operation 3 times, you could say that 180 degree rotation is just an operation associated with a C2 axis. So in actual fact, we can associate a C2, a C3 and a C6 with that principal axis through the middle of benzene, perpendicular to the page. And in actual fact, it's not limited to that either, because in the plane of the molecule, you could put an axis that cuts the molecule in half, going through two opposite vertices. And around that axis, you could rotate the molecule 180 degrees, and it would return to its original state. So you've got a C2 axis there. And with benzene having 6 vertices, you've got 3 opposite pairs, three pairs of atoms opposite each other through which you could put a C2 axis. So that's 3 of those C2 axes. But of course the other way of looking at it is that you could have a C2 axis bisecting the edges. And of course you've got 6 edges with 3 opposite pairs. So there's 3 ways that you could do that sort of C2 axis as well. So there's really quite a significant number. We've got 6 C2 axes altogether in the plane of the molecule, and we've got a C2, a C3 and a C6 that are perpendicular to the molecule. So we now ask ourselves, how many operations are there associated with these rotations? Well, all the C2 axes that we mentioned, there's just one operation associated with those, the 180-degree rotation. But with the C3 axis, as we saw before, there are two operations associated with that, the 120 and the 240-degree rotations. When it comes to the C6 axis, actually you've just got essentially the plus 60 and the minus 60, if you like, degree rotations. Or to put it another way, you can apply the C6 operation once or 5 times, two separate operations there. Of course, if you do it 2 times or 4 times, that's the same as the C3 operations. And if you apply it 3 times, that's the same as the C2 operation. So in terms of the total number of symmetry operations, I think we had 9 rotation axes altogether, 6 C2s in the plane of the molecule, and 3 that are perpendicular, C2, C3, C6. And then, in addition to that, the C3 and the C6 both have this second operation. So I think there'd be 11 symmetry operations altogether. And then the C1 symmetry element. What do we think of this? Well, this would be rotation by 360 divided by 1 degrees, rotation by 360 degrees. And that just seems trivial because, you know, you're not even moving any of the atoms in your operation. So it just seems pointless. But in actual fact, it's a bona fide symmetry element. It actually turns out to be a very important symmetry element. So important, in fact, that it gets its own special label, E, and it's called the identity element, or the identity operation. If you like, it's the do-nothing operation. And so we'll be referring to this quite a bit more. And next, on to reflections. And so in this case, we're using the Greek lowercase sigma to denote mirror symmetry, or a mirror plane in the molecule. And so you can see how symmetrical benzene is there. There's clearly going to be mirror planes involved. But actually there's more than one type of mirror plane, and they get labelled slightly differently. So it's worth looking at these. We've got a mirror plane holding the principal axis. So the principal axis will be the highest order axis. So in the case of benzene, that'll be the C6 axis, and it'll be perpendicular to the molecule. And so we do have planes, if you like, holding that axis that can cut through atoms in the molecule. And for it to be a mirror plane, it will have to cut through 2 opposite atoms, or 2 opposite corners of the hexagon. And so these tend to be called sigma V, the V being for vertical, as it's sort of aligned with that perpendicular rotation axis. But actually, as well as those planes that cut through the atoms, or the corners, there are also going to be planes which similarly, if you like, run along the C4 axis, but in this case actually bisecting the bonds, or bisecting the atoms, if you like, halfway along the edges. And so these ones tend to be called sigma D in their notation, D for dihedral. And the other type of mirror plane we can have is the one which is actually in the plane of the molecule itself. So that would be perpendicular to the principal rotation axis. And so if you like, any planar molecule trivially will have this sigma H, this horizontal mirror plane. So again, we can ask ourselves, how many mirror planes are there in the benzene molecule altogether? How many of each type? So we've just said there's going to be the one horizontal one, that is the plane of the molecule, sigma H. Then in terms of sigma V, the one which holds the principal axis, this is going to cut through 2 opposite vertices in the hexagon. So since the hexagon has got 6 vertices, there'll be 3 of these planes which cut across pairs of them. And similarly, where we're bisecting the edges, because we've got 3 pairs of opposite edges which we can bisect, there'll be 3 of these sigma D planes. So I think that makes 7 altogether. 3 sigma V, 3 sigma D, and 1 sigma H. And now on to another type of symmetry that is often talked about, the centre of inversion symmetry. And so we have this little eye to represent that. And so one way of representing that we can see in the illustration here with this octahedron, where the 8 corners are labelled 1 to 8, and we have the centre of inversion as the green dot right in the middle there. And so what's happening here with this operation is that each atom or each vertex in the molecule gets reflected through the centre of inversion. And so that would entail that you would draw a straight line to the centre of inversion, have it continue out on the other side as a straight line in the same direction, and then you would sort of map the original point to the same distance, the opposite side of the centre of inversion. And we can see that on the picture here. And so you can see on the right hand octahedron there, you see the 1 has moved down to the bottom, and that reflects how it's moved down to the centre of inversion and then out the other side the same distance. So similarly, 6 on the left has gone up to 6 at the top on the right. And in the equatorial plane, in the horizontal plane, again you can see everything's moved across. So 5 has gone from the far left to the far right. You can see that the 2 and the 4 have swapped places, and the 5 has swapped over with the 3. And then I was going to throw out the question that, in fact, this inversion operation can be achieved with 2 other operations. So I wonder which other ones they are. Perhaps not quite so obvious to see in the octahedron, but I think it is quite easy to see in this molecule which has appeared underneath it. And so in this molecule here, what we're going to do is we're going to assume the molecule's absolutely just fixed. We're not going to think about bond rotation or anything. So assuming the molecule is fixed in this orientation, you can see here, for example, the chlorine atom on the top left. When you do the inversion operation, you can imagine a straight line going from chlorine to the I dot there in the middle of the CC bond, out the other side, and it kind of reflects the chlorine through to the other side of the molecule. So you can see that this molecule, it's the same with the F atoms and the H atoms. So you can see that the molecule has this centre of inversion symmetry. But also the way it's shown like that, I think you can perhaps also see that there are a couple of other operations you do that will achieve the same result, kind of transforming the left hand, mapping the left hand atoms onto the right hand atoms. So you see that CC bond there, if you think about an axis running out from left to right through that bond, what you'd have to do there, you could do a 180-degree rotation. That would send the chlorine down to the bottom and the H and the F up to the top. Except of course the H would then be behind the page and the F would be in front of the page. And so that would be a C2 rotation. So half a revolution around that C2 axis. And then once you've done that and you've got the Cl at the bottom, you'll see then that the molecule has got mirror symmetry. And so at that point you can simply reflect the atoms in the mirror and they come out on the opposite side where the atoms are in the molecule. So you can see then that the C2 rotation followed by reflection in a mirror which is perpendicular to that C2 axis, that achieves the same thing as the centre of inversion operation. Now, onto a new type of operation, the so-called improper rotation. And when you first see it, it seems a bit bizarre because it looks just a bit kind of derivative, because it's saying that these operations based on a SN axis involve a rotation around the axis. So if it's an SN axis, then you have, if you like, an n-fold rotation around the axis, followed by reflection in the plane perpendicular to the SN axis. So of course this should sound very familiar because this is what we were doing with the centre of inversion. So in fact the centre of inversion symmetry is actually no different to the S2 axis using this definition here of improper rotations, S2. Now as it happens, it's always referred to as just little I, but it's worth bearing in mind that this is actually no different to just an improper rotation. Actually, another curious thing is that in fact the reflections that we looked at are actually no different to an improper rotation of order 1. So think about it, a rotation of order 1 leaves it unchanged, leaves the object unchanged, and then you're just left with the reflection, which of course means that the operation is just the same as a reflection. And so the S1 axis would be perpendicular to the mirror plane that you associate with a reflection. And this diagram below quite neatly illustrates an S4 symmetry with a tetrahedron. So you can think of this as being a methane molecule, if you like. And so in a methane molecule, there is no fourfold rotation symmetry. There's no simple symmetry in that sense. And you can see in the picture, the first thing you do actually is a fourfold rotation. So it's slightly fiddly to see here because we're trying to depict it in 3D. But you see what you're meant to see on the left-hand picture, the D and the C atoms there are meant to be kind of in a plane perpendicular to the page. And then once you do that rotation, so it's like a kind of clockwise rotation, you send the D up to the top and the C to the bottom. And then the A and the B, which are in the kind of vertical plane of the paper, once they're rotated, they rotate perpendicular to the plane there. So it's like A coming towards us and B going away from us. So that puts the molecule in a different position. But then when you reflect it through the perpendicular plane, which is shaded there in that sort of yellowy green colour, that green colour, it reflects through and then it comes out with the same orientation that it was before. So that shows you that a tetrahedral molecule, even though it doesn't have a simple fourfold rotation symmetry, it has actually got a fourfold improper rotation symmetry. So hopefully that there just kind of illustrates the point nicely about improper rotations. So now, some exercises looking at the octahedron. Starting off with how many improper rotation axes are there of each type on an octahedron. And of course, unlike the previous examples, we've got a platonic shape now. So actually, the octahedron is more symmetrical than it perhaps appears at first glance. These platonic shapes are all very, very symmetrical indeed. And you can see the octahedron has been shown in two different orientations there. So the one on the left is probably how we normally think of an octahedron. So you've got these four kind of equatorial atoms making up a square in the middle, and then you've got the axial ones above and below. That's how we normally think of an octahedron. That's how you'd often draw like the shape of an octahedral molecule or an octahedral complex. But the picture on the right is quite revealing, where we've just rotated the octahedron slightly, and here we're just focusing on the faces, because of course we have these equilateral triangle faces. And so when you look right opposite a face, you know, if the octahedron was transparent, you'd see the back face also triangular, but in sort of the opposite up-down orientation. But when you look through a face, there is symmetry around that axis. So actually you can certainly do a threefold rotation, because of course it's an equilateral triangle face and another equilateral triangle behind you, and when you do a threefold rotation, then it should leave it all looking the same. And actually that axis is going to be quite significant from the point of view of an improper rotation as well. So if you think about it, you could actually map the top face onto the bottom face using an improper rotation. So rather than doing a threefold rotation, which just turns the top face around so it looks like how it was before, if you rotated it by half that much, if you did a sixfold rotation, rotating it just 60 rather than 120 degrees, then you see that the top face would be rotated into the same kind of orientation that the bottom face is in. And if you then had a perpendicular mirror plane, that would reflect the top face right onto the bottom face after the rotation. And so that's quite interesting. There's a kind of sort of hidden sixfold symmetry there in an octahedron. And so that's one thing to think about, and how many axes of this type there'll be. Then the next question is, how many operations correspond to these improper rotation axes? And then finally, what about the symmetry elements and operations in total if you put them all together for an octahedron? And there's going to be a surprisingly large number actually. So what you could do here, you could pause it, have a think about it, come up with some numbers, come back, and then I'll take you on to the answers in the next slide. So here we are, the answers. So these improper rotations, remember I mentioned a moment ago how we have these six-fold improper rotations, and it was from looking through the faces. So of course an octahedron has got 8 faces, which means it's going to have 4 pairs of opposite faces, and through each of those pairs you can put one of these improper rotation axes. So with 4 of these pairs we can have 4 of the rotation axes, so there'll be 4 of those S6 axes. Also, slightly trivially, we have a 4-fold improper rotation axis, and so in a sense this isn't really much different to a regular 4-fold rotation, except once you do the rotation you'll reflect the top and bottom atoms into each other's position. And so these 4-fold rotations, they'll go through the kind of axial points at the top and the bottom and through the middle of the sort of equatorial square. But because of the high symmetry of the octahedron, actually you can pick any pair of opposite vertices and it looks the same. And so since an octahedron has got 6 vertices, there'll be 3 pairs of opposite vertices, and through each pair you can put an S4 axis. So there'll be 3 of these S4 axes going through these opposite pairs. Now as for the operations, a bit like we were saying with the C6 rotation axis, the S6 improper rotation axis will have 2 operations associated with it, a bit like you think of it involving a 60-degree rotation in one sense and a 60-degree rotation in the other sense. Curiously, if you apply the S6 operation twice, you don't end up with S3 in the same way that doing the C6 operation twice ends up with C3. And the reason for that is that when you do the C6 operation twice, yes, there are 2 6-degree rotations which would leave you with a 120-degree rotation, but the reflection, you do the reflection twice through that mirror plane, and obviously doing the reflection twice kind of cancels itself out. And so when you do the S6 operation twice, you actually end up with a C3. So we can't kind of invoke an S3 from that. Then you might think, it's the same thing if you do the S6 operation 4 times. That's the same as doing C3 twice. What happens if you do the S6 operation 3 times? Would that give you like an S2? Well, actually it would give you an S2, but that's what we call I, the centre of inversion. So obviously the 3 rotations of 60 degrees add up to 180 degrees, which would be a C2 rotation. And then each time you do one of those rotations, there's a reflection through the mirror plane. And 3 of those reflections, well, 2 of them will cancel out. It's the same as doing 1 reflection. So S6 3 times is the same as C2 followed by reflection in a perpendicular mirror. And that's the definition of I, S2. And then going on to S4, similar sort of thing. So the S4 axis is again associated with 2 operations, doing it once and doing it 3 times, which is like 90 degrees in one direction, 90 degrees in the other direction. S4 and S4 3 times. Of course, doing S4 twice, that's going to be the same as C2, isn't it? Because 2 90-degree rotations is 180 degrees, but you'd have also done 2 reflections, and so the reflections will cancel out. So it's just a 180-degree rotation, and that's the C2 operation. So there you go, the number of operations associated with these improper axes is just double the number of axes. And then this sort of slightly tricky one about how many elements and operations are there altogether. Well, what other things are there to consider? We could consider all the regular rotations. And so as far as C3 rotations, these are the ones where you're looking at the face on the triangle. Well, since we've got 8 faces on an octahedron, that's to say we've got 4 pairs, each of those pairs will have an axis going through the middle. So we've got 4 of these C3 axes. And as we said, each C3 axis can correspond to 2 operations, 1/3 and 2/3 rotations. Then again, with the C4 axes, these were both connecting 2 opposite vertices. So again, as the octahedron's got 6 vertices, we can have 3 of these axes running through them. So we've got 3 of these C4 axes. And so again, we can do a C4 in one sense, a C4 in the opposite sense, which would be like doing C4 3 times. But we can't do C4 twice because that'd be the same as C2. So each C4 axis has got 2 operations associated with it. And so we also have to consider the C4 axes as being C2 axes. So each C4 axis will also correspond to a C2 axis. So we have those additional C2 axes. But what's interesting is that we can find some other C2 axes here, and that is that all the C2 axes that we've been looking at so far, they've each been going through 2 opposite vertices. But we can also find C2 axes that don't go through any vertices at all. We can have C2 axes that just bisect opposite edges. And so if you think about it, an octahedron has got 12 edges altogether. And because of the symmetry of the thing, we can think of those as all equivalent, and we can think of them as 6 opposite pairs of edges. And there'll be a C2 axis going through each opposite pair. So there'll also be 6 of these C2 axes bisecting opposite pairs of edges. So yeah, quite a few of these rotation axes. Now going on to consider the reflection planes. Well, these C4 axes that we were talking about, that go through 2 opposite vertices, those axes are also in mirror planes. And we can have these mirror planes bisecting the edges in the kind of equatorial plane. So as those mirror planes kind of cut the octahedron in half, they can be cutting kind of halfway along the edges. So you can cut halfway along one pair of opposite edges in the equatorial square, and then you've got another one at 90 degrees doing the opposite pair of edges. So there's 2 of those sigma d mirror planes associated with each C4 axis. And of course there's 3 of those C4 axes. And in addition to that, another thing associated with each C4 axis, as well as those 2 mirror planes that hold the axis, there'll also be a mirror plane that's perpendicular to the axis. So that's in the plane of the 4 vertices in that kind of equatorial plane. And so yeah, on top of those planes, we've also got, of course, trivially the identity, where we do nothing. And there's also the I operation, which is actually the same as the S2 that we were talking about before. So altogether, if you add all those up on the page, no fewer than 34 symmetry elements and 48 symmetry operations. So it just goes to show how many you can collect with these platonic solids. And of course there are platonic solids with even higher symmetry than the octahedron. Now this is a bit of a strange thing, this will surprise you. We've been talking about all these types of molecular symmetry, but actually I'm going to just make the point, which I've kind of alluded to already really, that in a way you've only really got 2 types of symmetry, and that is to say proper and improper rotations. So how can I justify this? Well, do you remember we said the identity operation that we've spoken about, really that's the same thing as C1, like a 360 degree rotation, just leaves everything completely unchanged. You haven't even moved any of the positions around. And of course we said that reflections can be considered as S1 improper rotations, and indeed the centre of inversion as an S2 improper rotation. So it's quite a funny sort of, bit of a yin and yang, as you can see the symbol, way of looking at it. You can kind of consider everything to be one sort of rotation or another, a proper or an improper rotation. It's just quite a neat way of looking at it. And so I thought I'd finish looking at chirality. So I mean, you may have met chirality, but you might not have considered it in these terms. And so normally when we talk about chirality, often in the organic context, but we have inorganic chirality as well. But in the organic context, it's when a carbon is bonded to 4 different groups. And so when this happens, there are actually 2 ways that the molecule can be arranged in space, that the atoms can be arranged in space, giving us 2 isomers. And these are often spoken about as kind of right-handed and left-handed. And we talk of them as non-superimposable mirror images. And the handed thing is quite nice, because if you look at your hands in front of you, of course they're very similar to each other, but they're not identical, but they are mirror images. So you can think of if you stretch your hands out in front of you, think about a mirror in between the two, then when you look at your right hand in a mirror, it looks like your left hand. So they're mirror images, but they're not identical. You can't put your hands on top of each other, and obviously you'd have a thumb on one hand on top of a little finger on the other hand. And so we have these non-superimposable mirror images that give you a kind of right and left-handedness. And this is what we see if a carbon is bonded to 4 different groups. That's quite nicely illustrated here. So we've got a very simple molecule which has this feature. So this bromo, chloro, fluoro, methane here, that central carbon is bonded to 4 different atoms. And in fact that little asterisk there is used to denote this fact that a carbon is bonded to 4 different atoms. And so you see we've got a mirror next to it, and on the opposite side of the mirror we just see the reflection of the molecule. And it turns out that this molecule is different. And so one way this is nicely expressed here on the slide is that if you were just to rotate the right hand molecule in space so that the fluorine comes out on the right hand side, so you have the fluorine on the right, the hydrogen at the top, so you might think, oh, I've sort of reproduced the original molecule. But then if you compare that with the one on the far left, they're not identical. And that's because the bromine and the chlorine have been switched around. There's nothing you can do to make that mirror image superimpose on the original molecule. So there you go, they're non-superimposable mirror images, and this is what you find when carbon atom is bonded to 4 different groups. So you might ask yourself, well, supposing the groups weren't all different, supposing 2 of the groups bonded to the carbon were actually the same, so this would no longer be chiral. And what symmetry element would you associate with that state of affairs? So you can see that picture here. So this picture, a similar sort of molecule actually, except if you like, rather than having a bromine, we've got 2 chlorines. So think about if you change the bromine to a chlorine, so you have 2 similar atoms in the molecule. Can you see there that there's actually an element of symmetry in that molecule now? So what you could do is you could have a mirror plane that goes through the carbon and the 2 other atoms that are not chlorine, so that might be like hydrogen and fluorine, for example. You could have a mirror plane going through the carbon, the hydrogen and the fluorine, and that would be a symmetry element because the 2 chlorines would reflect into each other's position. Whereas the molecule with 4 different groups attached to it has got no symmetry associated with it at all. So that seems to be the key. Once you can put a mirror in the molecule, a mirror plane, then you lose the chirality, which is to say that with a mirror plane in the molecule, the mirror image would actually be the same molecule, it would be superimposable. But when you've got 4 different groups bonded to the carbon, no internal mirror plane, then the mirror image of the molecule is a different molecule, it's not superimposable. Now we can take this idea of chirality a bit further and look at molecules that have got multiple carbons with 4 different groups attached to them. And actually in this context, I should perhaps revise slightly the way I'm using the word chiral, because I think these days chiral is used to describe a whole molecule. And if you're talking about individual carbons bonded to 4 different groups, I think you'd call them asymmetric. So it is possible to have a molecule with 2 asymmetric carbons, but not actually to be a chiral molecule. That's to say there isn't a non-superimposable mirror image. And this is possible if there is an internal mirror plane. So we can see this example here. So if you look at the molecule on the left there, you can see that each carbon atom there is bonded to 4 different groups. And there is this internal mirror plane sort of bisecting that CC bond, a horizontal mirror plane. And so you see what we can do then is put a mirror to the right hand side of the whole molecule, and just look at the whole molecule in the mirror and see its reflection on the right hand side. So we ask ourselves, is this a superimposable mirror image? So the first thing you might do is you might think, well, let's flip the OH groups round to the right hand side. So you can rotate the molecule around, and when you do that, of course, now the methyl groups will be pointing behind the page, and so it looks different to the molecule on the left. But actually you can then flip it in the other sense, so you can switch the OH groups round, and by doing that the methyl groups then go from behind the page to in front of the page, and then this, you can see, shows that the two molecules are in fact identical. So this is an example of how you can have two asymmetric carbons in a molecule and yet the molecule itself not be optically active, that's to say not be chiral, not to have a non-superimposable mirror image, and these are called meso compounds. And actually I can't resist, there is an interesting kind of exception to this which links into what we were saying before about symmetry, and that is there's an interesting case of a molecule which has no mirror plane, no internal mirror plane, and so you'd assume therefore it would have to be chiral. But this molecule, despite having no mirror plane, in fact is not chiral either, and this is quite an interesting case. So it's this 1357 tetramethyl cycloocta tetraene. So you can see in the diagram on the right there the shape, and the thicker lines, the thicker bonds there are meant to represent the double bonds. You can see I've just had to correct one of the bonds in the picture on the top left. And so you see this molecule really doesn't have very much symmetry at all, and at first glance you might, looking at that, think perhaps the only symmetry in the molecule would be a vertical C2 axis, so you could do a 180-degree rotation, and that would take all the methyl groups round into the same position. It would leave the molecule, preserve that shape of the molecule. But the curious thing is we also have this S4 symmetry. So I mean, just to re-emphasize, you might think there are a couple of vertical mirror planes you could put in, but actually, while that would be the case if there were no methyl groups attached to the ring, the way the methyl groups are positioned in the ring means that you can't have the mirror planes. So there are no mirror planes in the molecule, but as I say, we do have this S4 axis. And so the S4 axis is a vertical axis, so passing through the middle of the molecule. And so you can see here that if you, for example, reflect the molecule in a horizontal plane perpendicular to that vertical S4 axis, then you get the molecule looking like it is at the bottom there. So you can sort of, we kind of flip that boat inside out. And then at this point, once you do the 90-degree rotation, the fourfold, around the fourfold axis, that does then take you into an equivalent structure to the one we started with. So there is S4 symmetry in this molecule, and given that S4 symmetry, we then don't have a chiral molecule. That's to say, it is superimposable on its mirror image. So that's just a neat little sort of exception to the rule being that you need a mirror plane for the asymmetric carbons not to lead to a chiral molecule. But what we can see is, strictly speaking, it's not a mirror plane, it's actually an improper axis of rotation. Because of course a mirror plane is an example of an improper axis of rotation, it's S1. But of course any improper axis of rotation will do this because it's got a kind of mirror symmetry built into it. And I think this builds me onto my just final comment I'd like to make about all this, and it's to do with really why we see this phenomenon in the first place and why this mirror plane is so important within molecules. And it's to do with the fact that the photons of light themselves are actually right and left-handed. We've spoken about these isomers being right and left-handed, these non-superimposable mirror images. It's a nice way to think about it. But the light itself, light carries a unit of angular momentum, and that angular momentum we can think of as having a clockwise or an anti-clockwise sense. You can sometimes talk about it as being a right hand circularly polarized, left hand circularly polarized. So it's kind of, you can imagine the photon going along like a sort of helix, and it can be like a right-handed helix or a left-handed helix. These are the two-handedness of the photons. And with the photons being handed in this way, they can kind of see the difference between right and left-handed molecules. One quite nice way of thinking about this is if you're shaking hands with somebody, Of course, if you put your right hand out, it makes a big difference whether the other person puts their right hand out or their left hand out. So as it were, you know, the handedness can sort of detect handedness in other things. So the right and left-handed photons can tell the difference between right and left-handed molecules. And so that's how this handedness, this isomerism kind of becomes manifest. And the thing is that, you know, when you have these right and left-handed photons or molecules for that matter, no amount of rotation can bring one form into the other. It has to involve some kind of reflection. And of course, the thing about improper rotations is that they do involve that sort of reflection. And so this is how, this is why we don't see the right and left-handedness in molecules if you have an improper axis of symmetry in there. So yeah, I just couldn't mention that a little bit at the end as it links up to our improper rotation.